you about. So a while ago, they invented probability, and it was really analyzed like gambling. Definitely the gambling came first. Then like we need some mathematical laws that model like rolling dice, and flipping coins, and dealing cards and stuff, um, which is great. But it turns out like the probability is just like not enough to model all the random phenomena that are in our universe. It only models a subset of the random phenomena in our universe. Which when you first hear it sounds like impossible. Like somehow you feel like by definition, like everything that's probabilistic is modeled by the laws of probability that we know and love. Um, but it's not true. Like here, like you can do like an experiment with these like two objects, like a cell phone and polarizing sunglasses that like illustrates this. You don't even really need the cell phone. You can just use the light. But I'll show it to you. I mean, everybody does this experiment on like, YouTube videos. So you've probably seen it before, but in case you haven't, um, yeah. So you can either use like polarizing sunglasses or you can use like the things that you get like 3D movies. You can do the experiment with them. So what you do is you get something like shooting out light. And cell phones particularly useful for this. And then like, let's see if I do this right. You put this like piece of plastic, which you get by like popping out the lenses of these glasses, like this. It like pretty much blocks all the light. Well, then if you put like another one like this, oh, it still blocks all the light. That's natural. But now if you do it in the opposite order, like you do this horizontal one first, you see like some light comes through, which is weird, right? Because like here, light is coming through, and now I'm gonna like move this one away. So you're like having fewer impediments. You'd think like only more light should come through, but like less light comes through. So it's like illustrating this phenomenon that like it matters the order in which you do these events, like this one first and this one, or this one first and then this one. So yeah, you can try it if you want. Here you go. You can just do it by like shining up to the light with like 3 of them, but if you have a cell phone, you can do it more easily. Yeah, so let me just to show you that like in like a diagram. This is your cell phone that's like shooting out like light. And so that's some light. This is my great drawing skills. And then this is like the piece of plastic that you can buy for like $1 or like pop out of the lens of a polarizing sunglasses. And like you pass the light through this and like it gets like fainter. And then you pass the light through the like diagonal version and it gets like more faint, but you still see some light coming through. But then if you exchange the order of these two things, you get like a different result. Okay, you shoot the light goes through this one, and that's the end of it. It's blocked. No light comes through, so definitely like no light gets to the end. Okay, so you get like a different outcome depending on what order you do these events in. And this is illustrating non-commutative probability. It's illustrating that the order in which you like measure these events makes a difference. And what this experiment that you can do doesn't like prove that like nature is non-commutative, but it is. It's just like illustration of the fact that like the real laws of probability that govern the objects here in this room are like a generalization of the laws you learn in probability 101. So you've only been studying a subset of probability for most of your life, unless you have already studied this stuff. So what do I call it like the basic probability? Why is that commutative probability? It's basically because of this. This is like why it's commutative. Like if you have a probability distribution P and 2 events A and B, and you like first condition P on event A, and then you subsequently condition that on the event B, it's the same as if you condition P on B and then condition that on A. Yeah, that's a true fact. Think you know why this is true? It's very simple. Well, they're both just P conditioned on A and B. You can just check this. So this is commutative because it doesn't matter the order you check these events. But in the real probability, it's non-commutative. So let me tell you a little bit like about the real probability. So in commutative probability, like you start with a sample space, which I'll keep it simple and make it finite. So it may as well just be the numbers 1 through D without loss of generality. And then in like non-commutative probability, you like upgrade this to a vector space of dimension D. Like going from like the Johnson to the Grassmann, like you take the sets and you like upgrade it to like vectors. It can be a complex vector space, but it's not important. Okay, that's sample space. And then like, deterministic state of some like variable is just like some I, which is like a number from 1 through D in your sample space. And then the generalization of non-commutative probability, like a deterministic state is a unit vector in D dimensions, called D. And then, general, probability distribution is like kind of like a convex combination of these states. But like it's not quite sensible mathematically to take a convex combination of these like, D objects. So you promote them a little bit to vectors. You like promote I to the I basis vector. And then a general probability distribution is just a convex combination of these EIs. And similarly, a non-commutative probability, like you want to like convex combinations of like the deterministic states, and it's not quite the appropriate thing mathematically to just take convex combinations of vectors. You promote them a little bit to matrices. This matrix VV transpose is like the projection onto the vector V. And if you take a general convex combination of those, you get like a general non-commutative probability distribution, if you will, which you usually write with like this curly-fied P. Well, I guess it's a row. And it has similar properties as like PSD, and like the diagonal entries add up to 1. Actually, in this talk, I'm not even going to talk about this like most general situation. We'll mostly talk about just vectors. Okay, so that's how you like upgrade like the most basic thing, sample space, to from commutative to non-commutative. And then like the second thing you learn about in like probability 101 is events. And what is an event? It's like a subset of the sample space A. Or if you think of an event as like a random variable, it's like a random variable whose values happen to be 0 and 1. So you can take A and just like think of it as a 0, 1 vector, these little A's, which indicate which outcomes are in the event and not. And in non-commutative probability, like an event is a matrix. And it kind of has to be like this because, we need some mathematical objects that are non-commutative. And the only objects we know that are non-commutative are matrices, right? So in non-commutative probability, like an event is like a projection matrix. It's projection onto a subspace. So you can just think of it like the event is the subspace or the projection onto the subspace. And it kind of matches because this is like a matrix whose eigenvalues are 0 and 1. Okay, and then the last thing you do in basic probability, like in the first lecture, is you glue these together and you talk about like what is the probability of an event A under a probability distribution P. And it's kind of like the inner product between like P as a vector and like this A as a vector. Or, it's like sum of Pi times AI. And the same story in the non-commutative world. So you talk about the probability of event pi under, the general state V. And you promote V back to a matrix. It's like this VV transpose. And you take like the matrix inner product between like this matrix and this matrix. There's like sum of pi ij, vi, vj. And so it's this. So you can forget about this middle part if you want and just take it as a rule that like the probability of event pi, which is like a projection, under like state V, so like a vector or a distribution V, is the squared length of the projection of V onto the hyperplane that pi is projecting. Okay, so this is like pretty much all you need to know for this talk. Oh yeah, sorry, there's one more slide. You need to know one more thing, which is about conditioning. So like if you have some probability distribution in event A, then you check to see if A occurs, and then like if it does occur, you get a new probability distribution, which is P conditioned on A, where you just basically take P and restrict it to the support of A, but then like you have to scale it so it adds back up to 1 again. And same story in non-commutative probability, you condition like a V on a projection pi. You need a new unit vector for V conditioned on pi, and it's just like you take V and you project it onto pi or onto the hyperplane, and then it's probably going to get shorter, so you like scale it up again, so it's a unit vector. Okay, I think that's it. Any questions? Okay, so this is the probability that like actually governs the world around us. It's like I didn't illustrate it, but it's like a strict generalization of the basic laws of probability. If you just take all the V's to be these EIs and all the projectors to just be like diagonal projector matrices, like projections onto the subsets of the EIs. Let's see how it fits into this like little cell phone story. So like here's my cell phone shooting out light, and so these like it shoots out like trillions of photons, and each one is in like this sort of generalized state. And it's actually all takes place in 2 dimensions. So this cell phone example is like d equals 2, kind of like bits. And so cell phones have the funny property that the vector v that they spit out is always this diagonal vector. Interesting. The light that's just coming out of here, it's all at random angles, but cell phones are designed to like shoot it out at this like 45-degree angle. And the reason for that is because roads, maybe lakes, are flat. So that's like a little puzzle for you. Like, what do like roads have to do with cell phones? But for some reason, the cell phone designers made it look like this, work like this. Okay, so it's generating like tons of like samples from this like same actually deterministic state, this diagonal state, and then these pieces of plastic that you can look through. These are like events. Okay, each one of these is like an event, So it's a projection on like a hyperplane, but we're in 2 dimensions. So it's projection on a line, and like the line is the one that's like it's a rectangle. So like it's like oriented like this. So this piece of plastic is like the event of projection on this horizontal line, and so we can call that pi1. And then if you like tilt it, then you get like another projector, which we can call pi2, which is projecting on this diagonal. Okay, so now we can just see like why that like little non-commutative experiment works. So the cell phone shoots out like millions and trillions of little objects whose state is kind of this deterministic diagonal state. And then like we kind of check this event vis-a-vis this state. And so the probability that the light gets through is like the squared projection length of this diagonal thing on this horizontal line. So this vector is like square root of half comma square root of half. So the projection is like square root of half comma 0. So the squared length is a half. So like half of these events like hit. So like half of the photons come through. And that's why the light getting through like one of these filters is like half as bright. Okay, but now here, like the new state is, is like the original state conditioned on pi1 happening. So that's like, you know, you take this vector and like you project it onto this line and stretch it back out to the unit vector. So now it's like 1 comma 0. And then you pass it through this new event, pi2. And you can see it's a similar thing. I didn't write b condition on pi1 here. I just wrote like horizontal vector. But the probability it will pass through here is like the squared length of the projection of this horizontal vector on this diagonal line, which is again a half. So again, like half of these photons make it through. And the ones that do make it through are like this vector conditioned on this event, which are these diagonal ones. And that's why finally like a quarter of the light comes through. But you see, if we reverse it, if we like do it in the opposite order, we get something different. So like here, this is it, because if you project this diagonal vector on this like other opposite diagonal line, the square projection length is 0. So like the event occurs with probability 0, and like 0% of the light gets. And you can see, well, yeah, like in linear algebra, right? Like projections don't commute. So this is what happens. Okay. Great. So when I learned this, I was like so excited because I love probability, right? But like everything in probability is like been done or it's like super hard. But now you realize that like the actual probability that governs our world is like a generalization. So you can just like try to like do everything that people have done in the past, but like in the real probability. So you can even like be like, let's tackle the union bound, like also like something you do on like day 1 of probability class. Actually, when I was Googling for union bound, I learned that there's a movie called Union Bound. It's about the Civil War. Apparently, it's a very bad movie. It's a 4.5 on IMDb, and you can tell because it was released in February. What's that? Yeah, yeah. Okay, so I don't recommend watching this, but maybe you have watched it. Anyway, I'm talking about this Union Bound, proved by George Boole in 1847. George Boole is, I also learned he's the great-great-grandfather of Jeff Hinton. That's kind of cool. It's a very interesting family. Yeah, so what's the union bound? Okay, I know you all know, but since it's the usual union bound, it's the commutative union bound. And it says like you have a probability distribution P and you have like n events and they're all like good events. You want them to all happen. And luckily, each one individually happens with probably 1 minus epsilon, only an epsilon chance of badness. And then what you really want is that like they all happen. And union bound tells you that it's very likely they'll all happen. They all happen except with probability at most n times epsilon. Okay, you can have different epsilons if you want and add them up, but like let's just stick to this. Okay, now here's a way that nobody would ever write it, but like, you know, in real life, when you check to see if an event occurs, well, an event occurs, you have to check them in like some order. So this is like a completely equivalent statement, which is that first, the probability that A1 happens under P, well, they all happen if and only if like A1 happens under P, and then A2 happens under P condition on A1, and then A3 happens under P condition on A1 condition on A2, and so forth. So this is equivalent statement. But like this is suitable for asking about the non-commutative version. So you could ask, like, is this non-commutative bound true, where we just change all the p's to v's and all the events ai to pi i's? This makes perfect sense, and it just asks, so like you have like a bunch of non-commutative events that are all likely to happen individually under the original, you know, state. Are they all likely to happen? Okay, so let's look into it. So by the way, this is like to say that the projection of a vector onto a hyperplane is like really close to 1 is basically saying the angle is really small. So 1 minus epsilon squared projection length is basically equivalent to angle being square root epsilon. It's really arc cos of square root of 1 minus epsilon, but asymptotically it's root epsilon. Okay, so like angle theta, it corresponds to probability 1 minus theta squared. Okay, so to get a feel for this, let's look at an example in 2 dimensions. So all the events are just projections onto lines. So we'll take our like cell phone vector, which is this diagonal one, and I'll give some example pi's, some example events. So here will be my pi1, and I'm gonna have all the events have the property that the probability of pi I under v is exactly 1 minus epsilon. So all the angles will be exactly root epsilon. So this angle right here is gonna be root epsilon. And then for pi2, I'm gonna put on the other side. So it still has the property that this angle from the state vector is root epsilon. That's going to be pi2. And then pi3, I'm going to put back over here. It's the same as pi1. And pi4 we'll put back over here. It's the same as pi2 and so forth. Like the odd ones will be on one side and the even ones will be on the other side. Okay, so let's see what happens. Okay, so first we check to see if pi1 occurs under v. And by setup, this angle is root epsilon. So the probability this occurs is 1 minus epsilon. Okay, and then assuming it does occur, that's this projection squared length is 1 minus epsilon. Assuming this does occur, like the new state is v conditioned on pi1, which is just the unit vector in this direction. Okay, and now we want to check like whether, let me go back here, oops, whether pi2 occurs. And now you see pi2's angle from the new state is 2 times square root epsilon. So this projection length is going to be like 1 minus 4 epsilon because of this squaring relation. So actually, the probability of event pi2 occurring under v condition on pi1 is actually 1 minus 4 epsilon. Okay, and if it does occur, then like this is the new condition state. And then you see, we check to see if like event 3 occurs. And again, like the angle between the state and like the hyperplane, the line is 2 root epsilon. So the square of that is 4 epsilon. So the probability that it occurs is 1 minus 4 epsilon. And so forth and so on. So like, it's true that they're all likely to occur, but like it keeps going back and forth across this angle of 2 root epsilon. And therefore, like the probabilities are all like, the probability of failure is like 4 epsilon, except for the very first one. So actually, the probability that they all occur is more or less 1 minus 4 times n times epsilon. So this shows that like the union bound doesn't hold exactly in the non-commutative sense. We at least lost this factor of 4. Okay, so if you're very optimistic, you'd be like, well, maybe this is the worst case. Like maybe this is a non-commutative union bound. And it's true. It's true. And this was proven in 2014 by Jinglong Gao. He was like a grad student at Xi'an University. I confess, actually, I had to look up where Xi'an University is in Xi'an. And isn't this cool? Like George Boole proved like the union bound in like 1847. And it wasn't until like this grad student in 2014 who proved like the real union bound, like the actual one that holds in our universe. That's pretty cool. Like you can be like the first person to prove the union bound. That's pretty good, right? Yeah. He wasn't the first person to consider it. Like, I'm not sure I totally have this history right, but like in 2006, Scott Aronson proved a worst bound where like the probability, this is showing the probability of at least one failure is at most 4 times n times epsilon. And Aronson showed that it's at most n times root epsilon. So it had n times root epsilon rather than basically n times epsilon. So it's definitely worse because root epsilon is bigger. Then 5 years later, Sen improved that so that the probability of at least one failure is at most 2 times root n times root epsilon. So it still had root epsilon, but it had the root n, it had the n on the inside of the roots. And then Gauss' result is just strictly superior because this number is exactly the square of this number. So like, this number is like always smaller than this number, or at least as small. And in fact, we saw by this 2-dimensional example, this is like exactly. So yeah, pretty cool. Yeah, what's up with this proof? It's not that bad. It's like 10 pages long. Although, the proof of like the union bound, the commutative union bound is like 10 characters long almost, right? It's like very simple. And like, this is not like a bad like screenshotting that I did. Like in this paper, like it literally cuts off the formula here and you just infer like what it says.
Wait, it does not appear at all? Like
what doesn't appear at all?
You can't read what happens?
Yeah. But it's okay. It's in the appendix. Yeah. Yeah, so I wasn't like too happy about this. So like me and this like undergrad, Ram Gopal Venkateswaran, gave a new proof in 2022 that's like about a page long. It's like, this is it. But maybe it's easier if you read some introductory stuff at first. Um, I'm still not like super satisfied with it. Like I remember when we finished this paper, I was like satisfied. Like how could it possibly be any shorter than this? But then on the other hand, you look at this and there's like trace of like the square root of like the square root of a matrix, and it's like I don't know. It kind of looks a little bit gross to be honest. So in the spirit of this, like maybe you should prove it. Maybe you should prove the real union bound. Okay, it's already proven, but like maybe you should give the best proof of the union bound. And this is a figure that's from that paper I had with Ram Gopal. I just put it up to illustrate the point that I'm like 95% sure that like all of the difficulty of this problem is contained in the three-dimensional case. So like all the events are just projection onto two-dimensional like planes, like good old planes in 3 dimensions. And yeah, it's just like you start with a vector on the sphere, and then you have like all these planes that are like at angle square root epsilon for this vector, and then you just want to like show that if you like keep projecting the vector onto this plane, that plane, this plane, that plane, this plane, that plane, like the vector can't get too short. That's the whole problem. So yeah, I would like to see you prove like or somebody prove like a proof that's as short as the commutative union bound. Okay. So in the abstract for the talk, I was like, okay, well now we're going to move on to Chebyshev's inequality proven by Pafnuty Chebyshev in 1867. Because yeah, you can try to like understand the non-commutative version of this like thing from like lecture 5 in probability 101. Unfortunately, when I was like making up the slides, I was like, there's not going to be enough time to talk about this. So just save it. You can ask me about it later. So the short story is that like last year I wrote this paper with Robin Kothari. It's like the non-commutative version of Pravesh Kothari. And it's like it's kind of like proves like a quantum version of Chebyshev's inequality. And like it's actually, I can, if you ask me about this, I can tell you like 2 sentences which like summarize like everything you ever need to know about like Grover's algorithm or like any other like quadratic quantum speedups that you may have heard about. They're all like this like just instance of like a quantum Chebyshev inequality. Okay, but I decided I didn't have enough time to talk about it just now. Okay. Yeah, so the third thing I want to talk about is a little bit more modern. It's Markov chains, invented by Markov in 1906. And actually, I'm going to spend a lot of time just talking about like good old classical Markov chains here. So here's a task, which I think is, I at least think this is a natural task. And it's like you should be in the spirit of like your computational complexity class when you're thinking about this problem, like complexity classes and stuff. So here's the task. You're given like a Markov chain, C, okay, on D states. And you're also given a parameter epsilon. And you want to sample from the stationary distribution for the Markov chain, the invariant distribution for the Markov chain. You want like a sample from a distribution which is epsilon close in total variation distance to the stationary distribution. Okay, and what's important is like how the Markov chain is given. It's not just like written explicitly like on a piece of paper like you see in like a probability 201 class. The transition is like given, it's implemented by a randomized circuit. So the input is like a randomized circuit, a randomized algorithm that takes as input a number between 1 and D and does some random stuff and outputs like a number between 1 and D. And that's like how you do one step in the chain. Okay. So there's certainly no trouble to like simulate this chain efficiently. But okay, you want to get to the stationary distribution, perhaps it would take a long time. So perhaps instead you should just look at the chain and somehow analyze things. Okay, so the question is, what is the computational complexity of this task? And funnily enough, like all the papers that, or almost all the papers that are on this subject, they're all like pitched from the story of like analyzing what would happen if you had like time travel, which is kind of funny. I mean, I think Scott Aronson kind of started this, but like this problem is exactly equivalent to the question of like, what would like computational complexity become if you had access to like log base 2D time traveling bits? So like, I guess like Gödel in like the 1940s like proved that it's consistent with like Einstein's equations that there are these things called closed time-like curves. And a closed time-like curve is like a loop in space-time that like comes back on itself. And as far as we know, these may exist in our universe, although we haven't discovered it. And then, yeah, it means that like if some bits can travel along this loop, then it's like they can travel back in time. And this guy Deutsch, the guy who basically invented quantum computing, uh, you know, kind of took this seriously, and he a little bit asked, like, okay, if we find one of these things, like, what is the, how would computational complexity change? And then like a bunch of people like wrote papers about this. And it's kind of fun. It's like good to like make your title of your paper be about time travel, but it's really, I am interested in this because I find this to be a natural question about not time travel, but like Markov chains. Okay. So let me give you an example to like warm you up to the concept. I'll give you an example where D is 2. So it's a two-state Markov chain. So C just like takes in 1 bit and outputs 1 bit. But okay, it might flip tons of besides epsilon. You might get this circuit. So the C takes in 1 bit B, and here's the code. So first, if the bit is 0, then first we're going to pick X. It's going to pick X to be a random n-bit string, and it's going to output D of X, where D of X is like some other circuit, a deterministic circuit that takes n bits and outputs 1 bit. Okay, so like the code for some other deterministic circuit with like n bits of input and 1 bit of output is like built into the code for C. I'm calling that D. So basically, C, if D is 1, it outputs like a random output of D. Otherwise, if C's 1-bit output is 1, then C will just like pick n squared random bits and output their OR. This looks weird, but I'm going to show you a picture in a second. Okay, so this is a randomized algorithm that takes in 1 bit and outputs 1 bit. So like it defines a Markov chain on 2 states, which we'll call 0 and 1. So let's try to understand like what's going on here. Let's first look at the transitions out of 1. So if like 1 comes into C, it's like more clear. Probably you just output 1 because the OR of like a bunch of bits is probably 1. You only output 0 with probably 2 to the minus n squared. And with probably 1 minus 2 to the minus n squared, you stay at 1. Okay, so this part is clear. Okay, and what's going on with the transitions out of 0? Well, the probabilities associated to the transitions out of 0 depend on what's going on with this circuit D. Okay, so in particular, actually, the probability with which you transition from 0 to 1 is exactly equal to the fraction of n-bit strings which like satisfy D, which make it output 1. Okay, and therefore, like, okay, the self-loop probability is a fraction of unsatisfying strings. Okay, so this is our Markov chain that we're presented with. And now let's think about, I mean, you have to know a little bit about Markov chains. So let's think about what is the stationary distribution for this chain. So suppose first that D is an unsatisfiable circuit. It always outputs 0. Then this arc has probability 0, and this arc has probability 1. So 1 is an absorbing state. So if you run this chain for a really long time, true, like maybe if you start at 1, it'll take a long time to jump to 0. But when it's jumped to 0, it stays there forever. And therefore, when D is unsatisfiable, the stationary distribution for this chain is like 100% probability on 0. Okay, on the other hand, suppose that D is satisfiable, at least one string makes it output 1. That means this arc has positive probability. And in fact, even if only one string satisfies D, this probability is at least 2 to the minus n. So you have like one of these classic two-state Markov chains where you go like across with different probabilities. But this is at least 2 to the minus n, whereas this is like much smaller, it's 2 to the minus n squared. So if you imagine running this chain for a really long time, rarely does it jump at all, but like when it's jumping, it's actually much more likely to be jumping to 1. So if you run the chain for a really long time, it spends almost all its time in 1. The stationary distribution for this chain, when this arc is probably at least 2 to the minus n, is practically 100% on 1. Okay, so like the stationary distribution like completely depends on whether this other circuit D is satisfiable or not. If it's unsatisfiable, the stationary distribution is 100% on 0. If it's satisfiable, it's pretty much 100% on 1. Okay, and that proves that this task we're talking about, like getting like a sample from the stationary distribution, is pretty hard. It's even when there's only 2 states, it's at least as hard as solving SAT, because you need to know like whether it's satisfiable or not, this D. It's also the case that like there's nothing special about 0 and 1 versus 0 and 1. So like it's also as hard as unsat. So it's at least as hard as NP and also at least as hard as co-NP. That's kind of a funny complexity situation. Okay, so this observation is kind of in Deutsch's paper, and it's kind of in this subsequent paper by Todd Brunn. And then, I mean, Aronson didn't phrase it in terms of Markov chains and stuff, but like basically from his thesis actually, he shows exactly the complexity of this task. It's this weird complexity class that probably you never heard of called BPP path. It's like a little bit bigger than NP and co-NP. It was originally defined, I think, in like a sort of for the authors, but a somewhat obscure paper from 2000 about the complexity of the stock market, and somehow they invented this class, BPP path. It's known to, under a de-randomization assumption, it's known to equal this somewhat more well-known class, P to the NP parallel, which is like all the problems you can solve if you have a SAT oracle, but you can only use it non-adaptively. Okay, so you like make a bunch of SAT queries all at once and get back all the answers. That's a class that's like a little bit above NP and co-NP. Okay, so that's cool. That's a cool result. I'll tell you a few more results on this flavor. I was once on a sabbatical in Turkey, and I worked with this cool guy, Jemsai, and we showed that for D being polynomial in N, it should be harder to solve this problem, but it's not really harder. Like it's still, the complexity is this weird class BPP path. And then actually earlier in 2009, Aronson and Watrous showed that for D equals 2 to the poly n, the complexity of this task is P space. And this is actually a natural setting because like when D is 2 to the poly n, it means like C takes in poly n bits. So like it's a polynomial sized input. You take poly n bits, but it's on a state space of size 2 to the poly n. So it's pretty natural. And for this problem, it's going to be P space. Okay, so this is all some background. Okay, so what about the non-commutative version? What I want to a little bit tell you about. So first of all, what is the non-commutative version? We would look at the non-commutative version of a Markov chain. So what is like a Markov chain? It's just like a way in which probability distributions can change. That's it. And the non-commutative generalization of this is called a quantum Markov evolution or a quantum channel. And has a mathematical definition, but it's basically any physical process that can occur in our actual world that transforms, d-dimensional general states is like non-commutative probability distributions to other d-dimensional states. Okay. It's basically some kind of like mixture of event measurements, kind of. Okay, so I'm not going to define it more than that, but it's just the natural way in which it's like the analog of a stochastic matrix. Okay, so you could ask the same question about this. So I give you like the analog of a Markov chain, a d-dimensional quantum channel, I, and some parameter epsilon, and you want to sample from a state that's the stationary distribution for it, from a state that's epsilon close in L1 norm to the stationary distribution for it. And again, phi is not given to you like as like a written down on a piece of paper, but it's like implemented by a circuit, quantum circuit. Okay, and actually, almost all the people that were like interested in this problem and like the time traveling bits and so forth, they were always like starting with this problem because they're talking about our universe and physics and like it's not just bits that could go around a closed time-like curve, but qubits could go around a closed time-like curve. So they always start with the non-commutative version, although I was like, let's start with the Markov chain version. It's easier to understand. But okay, let me tell you a little bit about what's known about this task, and it's summarized by some similar things. So for two-dimensional channels, like the simplest case involving like 1 qubit circuits, Aronson showed that the complexity of this task is exactly this other class, PP, which you might have heard of it. And this is in his paper where he gives like a new proof that this class is closed under intersection. And then a different paper with Jemsai, we showed that also the same story for polynomial many states. And also in this Aronson-Watrous paper, they showed that for exponential dimension, it's still p-space. So the non-commutative version is always like strictly harder than the commutative version. So a priori, this task could be like strictly harder to understand the stationary states for quantum channel. But they showed it's actually no harder. You can still do it in polynomial space. Okay. Let's go back to good old Markov chains for a second, because I like this problem and I want to tell you about an extension to it. So if you're a real complexity like nerd like me, then you might be interested in this question. Before I told you that like you have a Markov chain on like finitely many states, and it's like implemented by like some, I don't know, finite circuit, probabilistic circuit. But what if it's just given by like any algorithm, like a Turing machine, like a randomized Turing machine? And therefore, it can take an input of like, in sigma star and output something in sigma star. So it actually could be on like countably many states. And we don't like bound the running time or anything. You're just given like a little Turing machine, a randomized Turing machine. The only thing is, okay, you want it to like halt with probability 1 on all inputs. So you really have like it really defines like a probabilistic transition from like, I don't know, and from strings or numbers to numbers. Then what happens? What's the complexity of sampling from the stationary distribution of such a Markov chain? Okay, and this was asked by Aronson and 2 students in 2016. Okay, so we can ask this question. You're given a Markov chain it's like a Turing machine on countably infinite states, and you want to sample from a distribution which is epsilon close to the stationary distribution. What's the complexity of this task? This is a bit of a trick question. Does any of the like extreme Markov chain enthusiasts know why like there's some problem with this question? Yes? Yeah, exactly. Unlike with finite dimensional Markov chains, chains on infinitely many states don't necessarily have a stationary distribution. And yeah, it's really enjoyable, by the way. I don't know how much you're into Markov chains, but like usually when you learn about Markov chains in class, it's like finite dimensional ones, and it's like kind of fun. Although there's this weirdness about like irreducible or reducible, and like aperiodic and stuff. That they make these assumptions to keep things more easy. But anyway, every finite dimensional Markov chain has at least one stationary distribution. And they don't always talk about countably many states, but it's like fun stuff actually. So I'll tell you like 1% about it if you don't already know it. Actually, there's a very, very, very simple Markov chain that like on countably many states that has no stationary distribution. Just think of the states as like integers. And like on integer x, you output x plus 1 with probability 100% probability. So the chain just goes like, if you started at 3, it goes 3, 4, 5, 6, 7, 8. And it doesn't have a stationary distribution. Here's like a slightly more interesting one, though. It's a very famous Markov chain. The Markov chain where the state space is the integers, and you just do the simple random walk on it. You go like up or down with probability a half. This one also doesn't have a stationary distribution. Actually, if you're studying this, you come to make some, well, yeah, why doesn't it have a stationary distribution? Well, all the states are kind of the same. So by symmetry of the states, if it had a stationary distribution, surely all the PIs for the different states would be the same. But the PIs have to add up to 1. And like if the same value for the PIs is positive, then they would add up to infinity, which is a problem. And if the PI is 0, then they add up to 0, which is a problem. You just cannot have a stationary distribution. Okay. So if you start studying chains, there's some like nice definitions that you use to classify the states. So here are some definitions. A state I, like maybe the state 0, is called positive recurrent. You start at the state, and then you let the chain go for a while, and you see how long it takes you to get back to I. And if the expected time for that is finite, then the state is called positive recurrent. It means that, like, if you start at the state, like, expected constant time, you'll come back to I. And so you'll actually spend a constant fraction of your time in state I in the long run. There's another definition. A state I is called transient. If you start from I and you're like, I'm going to wait until I get back to I, if there's like a positive chance that you never get back to I, then the state is called transient. So I'll ask another question for the Markov chain enthusiasts. How about the state 0 here? Is it positive recurrence or transient? Yes? What's your positive recurrence? I don't think so, because if you start at state 0 and you walk for like a really long number of steps n, what's the probability you're back at 0 at the nth step? It's the same as like if you flip a bunch of coins, what's the chance that you like get exactly 50-50 heads and tails? It's proportional to 1 over root n. The probability you'll be back at 0 after n steps is 1 over root n. So in n steps, the expected number of times you'll be back at 0 is like sum of like n over root n. But this diverges. Actually, it's. Did I say that right? Yeah. It might take like a really long time to go out and come back. Somebody else want to answer? Yeah. That's right. Very good. Yeah. You have a Markov chain enthusiast. There's a third category. I mean, maybe I slightly tricked you into thinking there's only 2, but there's one more category, which is like the other category, and it's like null recurrence. So these are like funny states where like, you start from 0, like you're surely going to return to 0, but it takes like really long times, like on average, like infinite time on average. And it's not too hard to reason that like that's the case here. Okay, so there's this really like enjoyable theory of like Markov chains that involves these concepts. And for example, there's a theorem that a chain has a stationary distribution if and only if at least one state is positive recurrent. Okay, so we can just go back to this question and like ask like a revised version where like I give you a Turing machine that implements a Markov chain on countably infinite states, and I just promise you that it does have a stationary distribution, at least one. And now, like, what is the complexity of sampling from a distribution which is close to that? Or you can just say, like, I just give you some Markov chain and you have to do this, but if it doesn't have a stationary distribution, then I don't punish you, whatever answer you have. Okay, so this is like a reasonably interesting question, I hope, maybe. It's kind of natural. And so in this paper that we just finished writing with all these cool people, Aronson, Bavarian, Toby Kubitz, Avi Greywall, Peltrini, Marianne Rott. Okay, we exactly solved this problem. And it's kind of like the computability version of P to the NP. It's like it's this delta 2. It's like all those problems that you can solve in finite time with an oracle for the whole thing. Okay, so the class is like slightly above decidable. And actually, like for similar reasons, it's not too hard to show that this like it's at least as hard as solving the helping problem. Okay. And as a side theorem, this is not our main theorem, but like one thing we also observed is like for a different task, I give you a chain like this, and I also give you a state I, and I just ask, okay, is it positive recurrent, is it transient, or is it null recurrent? We show that this is like starting positive recurrence is sigma 2 hard, and transient is sigma 2 hard, and since this is like the complement of these, that's pi 2 complete, I guess. And it's a little bit funny is like these classes, this is like, you know, semi-decidable to the whole. So this class is strictly bigger than this class. So like actually sampling from the stationary distribution is somehow like fundamentally easier than telling if the states have these positive recurrent or transient or null recurrent properties. Here we use like some theorems that like some people in like programming languages that do this thing I don't know so well called probabilistic programming, where like it's a PL topic where like you're trying to analyze probabilistic code and they like prove theorems about it. Even though all these problems are undecidable, they still try to prove theorems about it. And yeah, we use like one of the results from this field here. Okay, so I'm not gonna like get very math heavy. It seems like it's getting towards the end of the talk, but I do want to tell you a little bit about the non-commutative version because again, like, you know, Scott was on the case. Like this is the problem that like they actually cared about. Like what about the quantum version, which is only strictly harder? Well, it turns out it's a similar situation. We showed that like even though it's like strictly harder or potentially strictly harder, it's more general. Like you can still do it in this complexity class. So you're still able to analyze basically the stationary distribution of a quantum channel on countably many dimensions that's given to you by like a quantum circuit in this complexity class. And all I want to say about this is kind of getting back to the theme of first half of the talk. Like, you know, in order to prove this theorem, like we needed to like use theory of like positive recurrent and transient and null recurrent subspaces for infinite dimensional generalizations of Markov chains. So like a Markov chain, they have all these positive recurrent and transient and null recurrent sets. And like now in the non-commutative world, there are subspaces. And so you need this theory. And unlike the theory for Markov chains, it's probably worked out like 100 years ago. Like this theory was only worked out over the last like 20 years. Like, I don't know, Veronica Umanita like did it for like finite. We kind of worked out everything for finite state versions not too long ago. And then the Italians are really into it. This person, Raffaella Carboni, like she proved a lot of great theorems. And then her PhD student, Girotti, like actually proved like the final thing that we needed. So the final ingredient we needed in this theorem was like from this person's work in 2002. And yeah, he was also a grad student. There he is right here. And he's working in Italy. And like kind of like his PhD thesis is like the maybe I think the last step more or less in like completing the theory of, you know, positive recurrent and null recurrent and transient for the quantum generalization of Markov chains. So again, it's like this flavor of like, you know, if you're sad that like Markov like did everything 100 years ago, you can do like the non-commutative version, which is like the real Markov chains that occur in our real life. And even in 2022, you can like solve these basic things. Okay, I have one slide about some open problem, and then I'm done. Yeah, so I said like once somehow I like understood this like vibe where, you know, like take literally any problem about probability and then like you have like a new problem to work on, like the non-commutative like real version of it. I got really excited and like you can do for like almost any problem. And like I guess these days, like what do people who like probability and like computer science, what are they into? I guess they're into like learning. So there's a lot of like nice open problems about like this kind of stuff for like learning and statistics problems. There's like a nice workshop on it just a few weeks ago at Fox. And Jerry Lee has this document on his webpage where you can see some nice open questions. I'll just like mention one, which is like my favorite. It goes by this weird name, shadow tomography, but it's just like the non-commutative version of like an extremely simple problem. So here's the commutative problem. You're given n events on a sample space 1 to d, just explicitly written down. Like you're just given n subsets of the numbers 1 through d. These are like events. But the probability distribution on 1 through d that you're interested in is unknown. You get samples from it. And you want to estimate the probability of A1 under P and also the probability of A2 under P and like the probability of all the events under P within plus or minus epsilon. How many samples do you need? This problem is super easy. I mean, if there was only one event, how many samples do you need of a probability distribution to estimate an event plus or minus epsilon, like 1 over epsilon squared? And then if you want, failure probability delta, then you need log 1 over delta over epsilon squared. And then if there's like n events, you have to union bound over n things. You need to take delta to be 1 over n, so you get like an extra factor of log n. So the answer is like log n over epsilon squared, upper and lower bounds, easy. Okay, so that's like in the subset of our world that's commutative probability, but what about the real version, the non-commutative version? Same question. You're given like n projections onto half spaces or hyperplanes, like n hyperplanes in d dimensions, just literally written down on a piece of paper as input. But like the unknown thing is the quantum generalization of a probability distribution B, and you kind of like get samples from that. And the same story, you want to estimate the probability of pi 1 and pi 2 up to pi n under the V, all to within plus or minus epsilon. So like a straight typo there. How many like samples do you need? It's at least as hard as the commutative version, so we have the same lower bound. Oh, this is also a typo. This should be an O. Sorry, this should be an O. The best upper bound we know is worse. It's worse on all 3 parameters. It's very annoying. Like it's log squared n, our upper bound, instead of log n. And it's got a dependence on d, which is annoying because this one doesn't. And it's got like this weird dependence on epsilon, like epsilon to the 4th. It's very annoying. Like I'm mad about this. I'm mad about this. I'm mad about like every aspect of this bound. So if you can improve like any of these things, it'd be very satisfactory. And the people doing quantum learning would care a lot.
You have a guess for a right answer?
A guess for a right answer? I can't guess, but like we don't know that it's not just this. Some people are really interested in just to know like if it has to depend on D at all. I really, really want to get like spend like I got like working with like the 10 brightest minds in quantum, like these young people for like a year, and we worked on like trying to get this 2 down to a 1. We made literally 0 progress. But I really want to get this down to log n because then it's really much related to like this hypothesis selection problem where you have like a huge collection of hypotheses and you want to pick the right one. It should really depend logarithmically on the number of hypotheses. But I don't know. Yeah, I don't know. That's it. Thank you. Questions? Time efficiency. Yeah, I always forget. I forget whether I guess this algorithm is maybe not computationally efficient. It's like only statistically, it's only a statistical bound. I don't quite know the story there. Yeah, it's a good question. This is very related to this like adaptive data analysis stuff, classically, where there's also some bifurcation in the trade-offs between like computational complexity and sample complexity. Any other questions? What's the debate? Maybe. I mean, like, uh, yeah, a little bit. So, like, I guess, like, it's more in the real world, like, it's mathematical name is event, maybe, but the real world is like a measurement. It's like a physical operation you do to like a physical object. Um, but like, it has two components. First, like, you like learn a classical bit of information, whether the event occurred or not when you do the measurement. And then based on physics, like either like the object just like goes away, or depending on like how it's physically implemented, like the object stays, but in like the conditioned state. Um, and maybe this is too like specific, and I don't understand this perfectly well, but with like the light filters and stuff, like it's kind of like a mix. Like if the event happens, then like the object stays and you see the conditioned version of the distribution. If the event doesn't happen, then like the filter just like eats the particle and like you don't even like have a state anymore. Yeah. Well, when you condition a distribution on an event, that no, like when you yeah. Yeah, like I guess the classically conditioning on an event changes the distribution. It could be, yeah. Just the laws of quantum mechanics. Yeah, I mean, the laws of quantum mechanics. Okay, I'm not a physicist, but the laws of quantum mechanics in like non-commutative probability are the same. Yeah. Yeah, I guess like to model things in the real world. Okay, I guess the real world is quantum that are based on quantum mechanics, and like the mathematics you use to model all the things that happen in the real world is this mathematical notion of non-commutative probability. Or one could say that. Yeah. And it's, yeah, that's right. But this is like these quantum channels. Yeah. Like, I guess if like probability distributions evolve in time, like stochastic matrices. Yeah. Oh, okay. Inversion of non-commutative Chernoff bounds. I don't know off the top of my head. Actually, when I said I was going to talk about Chebyshev bounds. It's not quite. It didn't quite fit into the like. It was a bit of a lie. Like it didn't quite fit into the story. It was more like um, using quantum algorithms on like classical probability distributions. So I guess I think there are like quantum versions of like Chernoff bounds, but I don't know them. I think if you like Google for like quantum coding literature, like all this stuff that this person Sen does, he might be the person to look up. Yeah. Uh-huh. Yeah.
Models related to adaptive data analysis.
Good question. So the quick answer is adaptive data analysis is like almost like this non-commutative version, except the A1 through AN are not given to you in advance. They come to you online from an adversary. The adversary tells you A1, and you can take as many samples as you want, maybe at the beginning, and the adversary tells you A1, you have to estimate, you have to report like your estimated probability of A1 under P, And then based on that, the adversary tells you A2. Based on that, the adversary tells you A3 and so forth. And there has more the flavor of the non-commutative stuff because the adversary, or like after you report your estimate for probability of P on A1 based on the samples that you drew, it's like from the adversary's point of view, the distribution on those samples has changed from the probability product distribution. And so the algorithms that like work in the adaptive data analysis version are like algorithms that are like much more sensitive to like the probability distribution changing and getting conditioned as like the events come in. And therefore, like the original quantum algorithms, in fact, like this also quantum algorithms, they're all like inspired by or like using some ideas from the adaptive data analysis world. So actually, all these algorithms also have the property that like you don't have to be given the events in advance; they can be given online because you're already using these like techniques that work well when the events get conditioned or you get conditioned on the events. But they also have like some funny things where like, you know, the first paper that had epsilon to the 4.5 or 3.5, and like they have log to the, like I think the best bound for that has like log to the 1, log d to the 0.5, epsilon to the 3.5 or something. Like they also have like weird bounds like this. Maybe not a coincidence. There's a cool paper by Mozart called Climbing a Shaky Ladder. And if you're like upset by like this epsilon to the 4th, like I am, like this is like the simplest like commutative setup where you can equally get frustrated by this epsilon to the 3 or 3.5. Oh, no, this algorithm uses, this is like cheating a little bit with the samples. This algorithm like measures more than, first of all, it measures more than one copy of V or rho at a time. So it doesn't use unentangled measurements. It's not like you get like a copy you measure, you get a copy you measure. It measures them in groups. So like that's an aspect of how it's like not very efficient in practice or maybe even in theory.
In some sense, in addition to sample complexity, also look at the final complexity. Depends how you create them up.
Yeah, if you know a little bit about quantum, like what really happens if you're going to use like m samples, what it really means is you get the m-fold tensor product of this v, and you can do like one giant event in this enormous d to the m dimensional space. And that's like the framework in which these work. It's not, it doesn't use it in the enormous space, but it still uses it in a pretty big space. And like there's a lot of practical interest in a lot of these like questions are about the framework where like you're not allowed to do this. Like you just get like every one copy, you can do like a measurement in d-dimensional space. That's like a restrictive algorithmic model, but it's like maybe more practical. I forget. Does somebody know? uh, you will get worse bounds, but I forget the story. Yeah, so this upper bound, I keep getting frustrated by the fact that I wrote an omega here by mistake. This upper bound uses entangled measurements on like multiple copies. I think, I'm pretty sure you, I can't remember. I think you can get like polylog n, polylog d, poly epsilon with unentangled measurements, but I forget. Okay, thank you.